Okay, so let us read the following theorem. Okay. So the binomial distribution tends toward the Poisson distribution as n gets larger, n approaches infinity, and p gets smaller, or as p approaches 0, while lambda, okay, which is equal to n times p, stays constant. Now, with this theorem, we can use the binomial distribution as an approximation to the binomial distribution when n is very large and p is very small. Okay, so for large n and for small p, we can approximate the binomial distribution using the Poisson distribution. Now, first, in order for us to prove the theorem, let us evaluate this limit. Okay, so let us go back to calculus, and we can try using L'Hopital's rule to evaluate this limit. Now, you can evaluate this using elementary concepts such as binomial expansion, or even the squeeze theorem. Okay, but I am going to use L'Hopital's rule. Okay, so we have okay, so let us first write our expression 1 plus x over n raised to n. Okay, now this is simply equal to e raised to the natural logarithm of 1 plus x over n raised to n. So by the laws of logarithms, so we have e. Okay, so this will this n will come down there, so you have n ln 1 plus x over n. So this is equal to e raised to, okay, what can we do with this n? Let us bring that down. Okay, so let us use algebra. So ln 1 plus x over n. Okay, so this n, we can write that as 1 over n. Okay, next we have let us use another page. Okay, so we have let us apply the limit. So we have the limit as n approaches infinity of e raised to our previous expression ln 1 plus x over n over 1 over n. Okay, so we next. Now, e is a constant. Okay, so e is a constant. So we can rewrite this as e raised to the limit as n approaches infinity of ln 1 plus x over n over 1 over n. Now, we can apply here L'Hopital's rule to get the limit of, now how do you apply L'Hopital's rule? Get the derivative of the numerator. So we have derivative of the numerator. So du over u, the formula is du over u. So derivative na of 1 plus x over n. So that is negative x over n squared all over the whole of 1 plus x over n. And the derivative of the denominator, derivative of 1 over n is negative 1 over n squared. Okay, so let us add another page. So we have is equals to, okay, so limit of by the way, this is being, we have a base e here. Okay, I'm going to go back to the previous page. Okay, so we have the base e. Okay, so next page. Okay, so limit of wait, let us go back to the previous page. So a fraction divided by another fraction. A fraction divided by another fraction. So that is negative x over n squared 1 plus x over n times n squared over negative 1. So we have e raised to limit of we can cancel this n squared. So let us cancel the negative. So everything becomes positive. So we have limit of x over 1 plus x over n. So next. So there is no longer need to apply L'Hopital's rule again. If you try to substitute, or if you make n tends toward infinity, this will become 0. Okay, so the denominator approaches 1 and x is a constant. X is a constant in terms of our limit here as n approaches to infinity. So x is constant. So we have e raised to, removing the limit, x over 1, which is simply equal to e raised to x. So this is the limit as n approaches infinity of our expression 1 plus x over n raised to the power of n. Now, we will use this result later on. Okay, now let us go back to the theorem. So what is the probability mass function for the binomial distribution. So the probability mass function is combination of n objects taken x at a time, or n choose x, multiplied by the probability of success raised to the number of occurrences of the successes, okay, multiplied by 1 minus the probability of the success raised to number of trials minus x. Okay, and then for the Poisson distribution, the probability mass function is given by lambda raised to x. Now, sometimes we approximate lambda by the mean or the mu. So, this could be your mu on some problems. Okay? So, lambda raised to x times the Euler's constant or the base of the natural logarithm e raised to negative lambda all over x factorial. Okay? So what will happen if we calculate the limit of the probability mass function, okay, for the binomial distribution or a binomial random variable? Okay? What will happen if we calculate the limit of this as n approaches infinity? Okay? As n approaches infinity. While considering this, lambda is equals to n times p. Okay? So, will it become what looks like the probability mass function for the Poisson distribution? Okay? So, let us try to find out. Ay, lintik. Meron pang sounds ah. Nagbibidyoke pa sa kapitbahay ah. Ay, nako. Okay, for our proof, we set n is equals to n times p, which implies that p is equal to lambda over n. Now, if we are trying to approximate the binomial distribution, we simply need to apply this formula. We set lambda equal to np. That is, again, if we are going to approximate the binomial distribution using the Poisson distribution. Now, for the proof, let us start or begin with the formula for the binomial distribution. So, remember, this is the probability mass function for a binomial random variable. Now, remember, we have set p equal to lambda over n. So, let us substitute. So, we have n choose x, or n objects taken x at a time. Then p is equals to lambda over n. So, raised to x. So, we have 1 minus, again, p is lambda over n. So, we have n minus x. Now, This is simply the combination of n objects taken n at a time. And we know the formula for this is n factorial over x factorial n minus x factorial. So we know that formula. And so we have lambda over n raised to x times 1 minus lambda over n raised to n minus x. Okay, so let us continue. So we have n factorial over x factorial n minus x factorial times, now I'm going to distribute the exponent x. So we have here lambda raised to x all over n raised to x, okay, multiplied by, so 1 minus lambda over n raised to n minus x. Now, I can combine or group these two expressions together. So let us do that. So we have lambda over lambda raised to x all over x factorial. Okay? So multiplied by n factorial over n minus x factorial. Okay, times 1 over n raised to x. So I group these two together, lambda raised to x and x factorial, and I grouped these two together to get n factorial over n minus x factorial times, I separated this from them, so we have 1 over n raised to x, and then we have the rest. Okay, now let us try to expand this. We will let us concentrate on this first. Let us see what will this look like if we expand this. Okay, so let us try to expand this term here. So let us rewrite the others. Now remember, n factorial is simply n times n minus 1 times n minus 2 up to 2 times 1. Okay. But then again, we can use a trick here that we are already familiar with in order to cancel the denominator. Okay, we can instead of bringing the numerator down to 1, we can simply write let us erase some terms. Okay, so we can simply make n factorial be the product of n down to n minus x. Remember, x is less than or equal to n. And then down to up to 2 times 1. So we need the factorial symbol here. Okay? Then let us write the rest of the expression. So we can now cancel out n minus x factorial. And then let us combine the result with 1 over n raised to x. So we have lambda raised to x over x factorial times. So we have n times n minus 1, n minus 2 times what? Times n minus x plus 1 all over n raised to x. Oh, why up to n minus x plus 1? Remember that we have here a factor which is 1 greater than n minus x. We have here n minus x plus 1. Okay? So the rest 1 minus lambda over n minus x. Now, how many terms do we have in the numerator? So we have here x terms. Now, how many n's do we have here in the denominator? So we have x number of n's. Okay? So let us expand the denominator a bit. So we have here n times n times n. How many n's? We have x number of n's. Okay, so let us go back previous page. So we have on the numerator n times n minus 1 times n minus 2 times up to n minus x plus 1. So let us go back to the previous page. So we have here 1 minus lambda over n minus x. Okay, let us check first before we move on. Okay, so 1 minus lambda over n minus x. Okay. So let us continue. So we have here x factorial times n over n times n minus 1 over n times n minus 2 over n times dot up to n minus x plus 1 over n times 1 minus lambda over n minus x. So what do we get? So lambda raised to n over x factorial times, so this is simply 1 times, so this is 1 minus 1 over n, so this is 1 1 minus 2 over n dot dot dot. So we have here up to 1 minus what do we have here? 1 minus x minus 1 over n multiplied by 1 minus lambda over n and n minus x. Okay, so we need another page. By the way, we can write this as the whole of this expression as 1 minus lambda over n raised to n multiplied by 1 minus lambda over n raised to negative x. Simple law of exponents. Now, back to our formula for the binomial distribution. Now, let us take its limit as n approaches infinity. Now, we have already expanded this. We know that this is equal to that very long expression. So, limit as n approaches infinity of lambda over x factorial multiplied by 1 minus 1 over n (1 minus 2 over n) let us use an ellipsis here. So dot dot dot. I'm going to look at the previous page. So we have 1 minus 2 over n up to 1 minus x plus 1 over n. Okay, so let us continue up to 1 minus x plus 1 all over n. Okay, let us take a look at the previous page. Then 1 minus lambda. Let us enclose this within a pair of brackets. Then 1 minus lambda over n raised to n. 1 minus lambda over n raised to n minus k. Next, remember that this is a product of many terms. So what is our rule, limit rule? What is our limit rule? We can simply take the limits of the factors. Okay? Now, let us examine this one, this factor. Now, we are taking the limit as n approaches infinity. Limit of n, not lambda, not x. So, this is a constant. So, we have lambda over x factorial. Now, how about the limit of this? What is the limit of this? As n approaches infinity. Okay, the limit of this is what will happen as n approaches infinity? 1 over n becomes 0. 2 over n becomes 0. This becomes 0. So you have 1 minus 0 is 1. 1 minus 0 is 1. and then up to 1 minus 0 is 1. So the whole of this is 1. So you have times 1. Okay? So next, oops, I have over erased. So next, so what is the limit of this as n approaches infinity? So limit of that, limit of 1 minus lambda over n raised to n as n approaches infinity. So this is simply equal to e raised to negative lambda. By that expression we have evaluated earlier. We have evaluated this at first because we're going to need this. So now, now we have used it, to simplify this expression. So we have here e raised to negative lambda. Okay? And then finally, look at the last expression. So what is the limit of this? By the way, we have an extra ender. Okay. So that is negative k. Negative k only. Okay. So what is the limit of this? Okay. Remember, as n approaches infinity, lambda over n becomes 0. So we have here 1 minus 0. So that is 1 raised to negative k. So it's still 1. And finally, we can simplify this as lambda times e to the negative lambda all over x factorial. Thus, the limiting form of our binomial distribution is the Poisson distribution. Look at this expression. Okay? So from our probability mass function of a random variable of a binomial random variable, okay, we got the probability mass function for the Poisson distribution. So again, the limiting form of the binomial distribution is the Poisson distribution. And we have completed the proof. So good day. Sarap ng field trip ah. Okay, we have an erratum. So this is still x. This is x minus 1, not x plus 1. Okay? So this is x minus 1. But the results did not change. Okay, so let us so where is that? Okay. So here, so this is x minus 1. X minus 1. Okay? But the result is still the same.